Okay, cool. I will actually have to say the title of my talk. You'd think I'd know better by now, but I really, really don't. Cool auto subtitles, so all my vocal tics get transcribed in real time as well. So clouds, microservices, and the brittleness of architecture, or why your cloud architecture might kill your software. So, amazing, it does work.
Or yourself.
Yeah. So that's me on a boat with overproof rum, which is living my best life. I'm a freelance consultant, and I've worked with lots of fun places that write fun software. So I was previously the chief technical architect of JustGiving, the head principal engineer at the Trainline, vice president of engineering at a company you've never heard of called GFK. They're all silly job titles, but the one commonality is that all of those organizations were big, air quotes, web scale people out of the UK, and they all engaged in re-architecting for the cloud while I was there. So I had the, we're gonna go with good fortune, good luck, poor luck, of having to barrel roll through 1,000 cloud migrations for consumer things. I actually quit all my jobs 3 weeks ago, so I'm now just a professional Twitter shit poster, but it doesn't pay as well. So it's 2015 and you've read a bunch of things about Netflix and Spotify. This is normally the start of most people's cloud migration stories. And yes, we know AWS landed in like 1854, but nobody was using it until about 2009, realistically. And all the blog posts said, microservices, clouds, infinite scale. Hey, have you heard of the Spotify model? And your CTOs and your MDs and your CIOs, and nobody actually knows what CIOs do other than babysit CTOs, were like, oh, Spotify model. We've heard of Spotify. People like music. Can we do that in our software? But actually, everyone stopped reading all the articles before they got to all the good bits, which was really, really ironic. So in literally February of 2015, Netflix were saying things like, create separate data stores for each microservice, keep code at similar levels of maturity, do separate builds for each microservice, deploy in containers, treat servers as stateless, cattle not pets. And Spotify were most importantly saying, aligned autonomy. So aligned autonomy is a really interesting phrase, and we're going to come back to it later. But what everyone really heard was kind of developer anarchy and shiny new toys and, oh, we don't need the ops team anymore. It's a bit awkward for the ops team, which is great. They just rename themselves SRE and have a job for life, right? So cool. So your boss tells you you're converting to microservices because all technical migration should obviously be done top down. Don't know whether sarcasm comes across in the video recording, but /S. So clouds, microservices, and Docker, and you thought, yeah, well, I'm currently struggling to ship this one thing that we have onto like the 3 web servers that I'm shipping it onto. So yeah, let's break that into loads of little pieces, and it's going to solve all my problems. People said this all the time. So microservices and infrastructure tooling like containerization is only useful if it actually helps you solve problems, rather than create entirely new categories of them, which is awkward. But regardless, you've decided to rewrite the monolith into a suite of microservices. You too shall go to the ball. But if you can't ship your existing monolith, you're literally fucked if you try and ship microservices. You get absolutely, sorry, does anyone mind if I swear? This is going to go really badly otherwise. So if you sketched out your target architecture and some guy with like a job title like I used to have draws a diagram and he says, oh, this is what we're doing now. You're like, okay, cool, I've still got my one binary. So let's think about this a little bit. So your microservices are just as prone to Conway's law as your monoliths are. And people are slowly starting to come around to this realization now. So let's think about what Adrian Crockford originally said when he defined microservices. Loosely coupled, service-oriented architectures within bounded contexts. Sounds a lot like DDD. Today I learned I like pink gin. So yeah, when most organizations tried to re-architect towards microservices, they either ended up building SOA services over legacy monolithic data stores. I saw that a lot of times. One system, one database, now 100 systems, one database, all falls over together. with horizontal slices across existing applications. And if anyone was around in about the year 2000, that was just SOA. That's not microservices, it's just SOA. That was the point. And really, microservices are the evolution of 2000s era SOA via Gorilla SOA. The other anti-pattern that people fell into was this wonderful cacophony of interdependent domino-like nanoservices. And it's really, really simple. You can tell whether you've got domino-like nanoservices by just taking one thing down. Like if you turn one thing off and everything else falls over, not a microservice architecture, just a distributed one big ball of mud thing. And the vast majority of the systems that weren't SOA were nanoservices. And this was, at the start of any technology trend, people fall into the obvious problems, and these are the two big obvious problems. Ironically, Spotify had the right idea from the start when they said aligned autonomy, where squads build aligned to strategic themes. Again, sounds really suspiciously like domain-driven design. So you're now in the cloud, and things actually aren't better. In fact, in many cases, things are a little bit worse and ironically more expensive. Your road to the cloud is a rocky one, fraught with the poor specification of it's just a lift and shift. You deploy out, and the first time there's any kind of hosting infrastructure outage, you go down hard, like really hard. And you get hauled into the office of the CTO or CIO, and they say, oh, well, we moved to the cloud. We heard it was like infinite scale. And you're like, yeah, but we didn't really read the bit about multiple availability zones in the docs, so actually we were just in a data center. Awkward. More for you, because it wasn't in your target architecture. Because designs don't come from paper. And oh, by the way, when you come back up, you need to patch all your Docker images now, because they all have security vulnerabilities, and now there's 200 of them rather than like 3 PCs. Awkward. There must have been an easier way for all this. There must be an easier way. So, firstly, and this is a little bit, I wrote this originally for like an Azure conference, and this is a little bit me wailing on AWS for being hot garbage. I really shouldn't quote things like that on recorded footage, but AWS is hot garbage. And everyone seems to love it, but it's really, truly awful. Infrastructure as a service, like, get out here. There's no dumber thing than just replicating your existing data center in fake computer programs that are pretending to be your existing data center. You're not getting anything from any of that. Infrastructure as a service is a pox on developer productivity. It's the devil, it's Lord Belial, it's Lucifer, it's Old Nick, it's the literal fucking worst. You got a DevOps team? Yeah, you got a DevOps team? Nice bottleneck you've got there. Like, cool, really, really great hiring you did there. Very progressive, because you called it DevOps rather than Ops, but it's still a team in the middle that looks after your servers. So not really DevOps, is it? Because DevOps is an engineering culture, not a team. Infrastructure as a service is a hellscape of configuring scaling and virtual load balancers and configuration of network-attached virtual disks. There's no disks. These are all computer programs. Yet we're pretending like we're plugging in cables. Oh, and don't forget deployment tooling, because all of those things you get for free in well-designed platform as a service abstractions, you're going to have to build your own. Or you fall down that whole like, oh, well, we do Kubernetes, and then we install Helm and a bunch of other monitoring tools, and now, it's just actual fucking hell. So committing to an infrastructure as a service platform to build software is just deciding to spend a literal $1 million on tooling yourself. That's all it is. Nothing more sophisticated than that. And people always kind of scowl at me when they say that, because like, oh, you're wailing on the cloud. I'm just wailing on AWS for not innovating in a decade. So to labor the point, you want to build a message-based architecture and you're doing infrastructure as a service, you set up RabbitMQ 3 times, or Kafka, and like the 300 crap dependencies that come with Kafka, 3 times in 3 different availability zones. Oh, and then like once each time for like your dev and your QA and your test environments. And then you've just got a queue. Cool. Or you go on something like Azure with a good platform abstraction and you click create CosmoDB account and you're done. Right? Like it's really just a waste of money. There's actually an interesting story that's not part of the slides, but we're going to tell it now because it's really relevant. I was working on a project recently where we had a big Kubernetes install, and we were migrating it from AWS to Google's managed Kubernetes. The bill for the Kubernetes cluster that ran the piece of software that didn't ship in 12 months, that had 0 users, was 25 grand a month to run the Kubernetes resources and workers. I replaced it all with a single GCP App Engine app that cost £3 a month. 25 grand a month to £3 because people thought they wanted the control of creating pods and keeping a team of 9 SREs in jobs. True story. So vast amounts of companies have moved to the public cloud in its decade of general ability, 2 decades of general ability, whatever we count it as. Migrating now is an outlier. You're probably not going to be migrating to the cloud, but a lot of companies are in a hybrid situation now rather than migration. And the simple truth is that when you move to the cloud, you need to think about where your software is and where your software design is, where it goes. Because the cloud, and if you're designing software to work resiliently in the cloud, the nature of what is your software, is your hardware your software now? An interesting question. So I don't mean where is your software physically located. I mean, where is your software architecture? Where is it? What do you do to make your software run well in a cloud-native environment? How do you run this stuff locally? How do you debug this stuff? So there's some true north qualities of excellent software design. Readability, debuggability, source controllability, visibility, legibility, observability. Right? These are all the qualities you're looking for in good software. But if you can't run your software on a desktop machine or a laptop, how are your devs going to build this stuff? And I've seen lots and lots of systems get distributed to the point where no one can actually run the system anymore, and it's really, really dangerous. It kills companies. So we have to talk about this concept of cloud native and what cloud native really means. So when we talk about cloud native software, we talk about software that's designed to operate in a distributed manner as part of its very makeup and DNA. Software that's aware of both the advantages and shortcomings of the public cloud. Now let me preface this by saying I love the public cloud. I've not shipped to a data center in 15 years, realistically. But cloud native isn't containers, though all the container vendors will tell you it is. Cloud native isn't rebuilding for the cloud, despite what all the consulting firms will tell you it is. Cloud native is building or rebuilding portions of your software so they can live in a disconnected, dubiously available, sometimes flaky, sometimes distributed environment. Cloud native is not Docker or Kubernetes or Azure App Services or GCP App Engine. What you really wanted was to build these kind of native applications, and you want it built on a platform that gets the fuck out of your way. Sorry, I can see you out of the screen go. The beautiful crows. And everyone is like, oh, well, what the hell actually is a cloud-native microservice then? If it's not any of those things that I thought cloud-native meant, then what is it? Cloud-native microservices are loosely coupled services around bounded contexts. Simple as that, and we'll go through some examples. The services that expect failure by default, and the services that are built to cope with the bumpiness of mostly online and mostly available. Because the truth is, when you're building cloud-native applications, runtime failure is no longer an edge case. Availability zones will go down. Connected storage will disappear and get recreated. Your vendor will roll random operating system updates that are meant to be invisible across whatever stuff they're running underneath, and it will affect your software. You're going to see this. A great cloud platform like Azure, or actually GCP is pretty good as well, is a wonder to behold. It's a blue sky of developer productivity where we try and remove all the barriers between writing code that solves problems and shipping it. That's the purpose of the cloud, to take away all the things that make shipping code hard. But what you have to do is accept this degree of unpredictability along the way. When failure is not the edge case, you have to design for it, because this is now a software concern once you're in the cloud. If you're building event-driven systems, where's your replayability? You need to build replayability or use services that provide replayability. If you're building services that interact over HTTP, do you have resilience and fault tolerance and backoff? because you need all of those things. You're designing HTTP services. Do they support idempotent retries? And none of the cloud vendors solve these problems, which is why they get everybody, because these are software concerns. They're design concerns of your software, not how are we shipping a bunch of containers onto some infrastructure. They're literally not ops. Oh, and the really good thing that'll get you, especially if you're blowing up some kind of monolith into microservice architecture, is you probably didn't think about latency. And latency got every single one of the cloud project migrations I've ever worked in. So you know all of those services you built? Well, I understand that once upon a time they were part of the same application. So all those method calls with 5 nanoseconds latency between them, or 2 CPU cycles of latency, they're now all 1 to 10 millisecond calls. That's so many orders of magnitude slower. You just slowed your whole system down. Sorry, and it all adds up. So how do we stop this happening? How do we stop the stem of blood? How do we stop us bleeding out as we blow up these systems? Because I still thoroughly believe that building microservice architectures is the right answer in a lot of cases. It's the right thing to do. So what we need to do is we need to invest in real, proper, battle-tested cloud software patterns. So let's talk about a few characteristics of some well-designed cloud-native applications that help them deal with this kind of uncertainty. So you're going to end up with circuit breakers everywhere. Has anyone ever implemented the circuit breaker pattern in here? Hands up. Okay, cool. So the circuit breaker pattern looks like a really complicated diagram, but is actually really, really simple to understand. It's the model of an electrical circuit. So you make a request to something. If the request fails, your circuit pops open like it's blown a fuse. So what you then do is you stop sending more requests down that channel, whatever the channel is, be it HTTP requests or, I don't know, sockets, what a website, I don't know what people use. HTTP requests, it's always HTTP requests. Come back. And then after a predefined timeout, you send one request through. And if that request fails again, you leave it open and reset your timer. If the request succeeds, you then close the circuit, and all those requests you deliberately didn't send, you let flow through the circuit again. So it's a way to meter your failure. And the interesting thing is, the circuit breaker pattern is normally used to protect yourself from the failure of external systems, of other people's stuff going wrong. In a distributed environment, all your stuff is also the stuff that's going to go wrong. So you have to implement these patterns within your own systems because, well, when it was one process, it fails together. When it's 30, who knows? All bets are off. So in a microservice architecture, your services could be those broken systems. Please defend yourself from your own outages. The other thing the circuit breaker pattern does quite well is it stops you sucker punching yourself offline. If one of your services go down and you just keep on fucking sending the requests, so every time it gets back up, you kick it. It's great. Queues everywhere, which is kind of the other half of the circuit problem. So retrying calls becomes a reality. You've got to presume everything is disconnected and everything is offline. What happens if your vendor decides to do a rolling update across one of your services and you didn't configure the appropriate level of redundancy? You just lose your data. Sucks. So you need to support resilient retrying. And a lot of queuing libraries or queuing implementations will have this out of the box. I mean, Christ, MSMQ had it out of the box. This isn't posh, but it's essential. You need to think about backing off so you don't kill your own services, because much like not circuit breaking, if you have a queue, you could. This was like a year 2000 computing problem that originally Memcache was invented to solve by, I think, Brad Fitzpatrick, who worked on Go most recently, but built the proto-blogging platform LiveJournal. Trivia. And the problem was, when a service is down, everyone's retrying. When the service comes back up, everyone's still retrying. So if you've got a service that needs to warm up or load some data or do anything, most of the time it just gets sucker punched straight back off the internet by all of the clients turning up at once. So queuing can be throttled, and you can drip feed those requests back through. So you can design your systems so they can self-heal by using these patterns. Actually, I missed a bit. Oh no, that's fine. We got something else with the stampeding herd pattern. So competing consumers for parallelization. That's a mouthful. Probably shouldn't have that on the slide. So multiple queue consumers builds resilience into a system and increases parallelism. So the great thing about competing consumers in a single queue is you just put all the stuff in the queue, and if half of them go offline, cool, your system just gets slower. That's okay, because you're not offline. Being slow isn't offline. And actually, you find with a lot of distributed systems, the notion of what counts as on and offline. Like I was having a conversation in a pub a couple of days ago about this, where we were talking about the notion of the 5 nines. And everyone's like, oh, we do 5 nines uptime. Sorry, bullshit. I've seen like 3 companies that ever have done fucking 5 nines uptime. Most people go down for like a day, a quarter, easy. Like this stuff happens in the real world. But if it's like only a portion of your microservice architecture that goes down, like does that really count as really down? I mean, you can probably still get 5 nines if they could load the homepage, right? Or just about check out at the till. Like no one, you can't fail your KPIs that easily. So an application running in the cloud is expected to handle a large number of requests. Rather than processing each request synchronously, a common technique is for the application to pass through a messaging system to another service, a consuming service, that handles those messages asynchronously. This strategy helps ensure that the business logic in the application isn't blocked while the requests are being processed. And the really cool thing here is this is literally the design pattern for scale out. Like you got a queue, you got one queue reader, you need it to go faster. Add another one. It scales linearly, it's not complicated. All the big things that the architects pretend are really hard, it's just another process, it's fine. And I suppose the opposite, throttling and auto-scaling also. So the load on a cloud application typically varies over time. This is the truth. And based on the number of active users or the types of activities they're performing, the load is always very, very uneven. So it's a good idea to be able to throttle and scale down. So here's some trivia for you. Back in about 2013, Just Eat, every dinner time, used more AWS than Netflix in Europe. In the daytime, it was like a homepage running on one server. At dinner time, you basically had your own AWS server to order your own pizza on. They flexed up that hard. Because I remember working on some of the software that bought lots and lots of machines, and we ended up breaking AWS's bidding process for Spot instances at one point because we had so many of them. I'm not going to say it was perfect design at the time, but hey, it worked. You got your pizzas, right? So there are many strategies available for handling varying load in the cloud that depend on the business goals for the application. One strategy is to use auto-scaling to match the provisioned resources to the user needs at any given time with a bit of sensitivity towards warm-up. The great thing, again, if you want to do this in IaaS, or even, Christ, doing this in Kubernetes isn't even very easy. Like, for the great white hope that it pretends to be, it really isn't very good at this stuff. Azure, Heroku does this brilliantly. You know, this is 10-year-old tech. But scaling up and scaling down becomes important because the cloud is, and they don't really talk about this, probably more expensive than your data center. So if you're not using the ability to scale back down, you're actually just paying more money for the same stuff. I mean, you get a lot more for it. Bulkhead isolation. Now, this is one that people often don't hear about. So the diagram there is kind of fun. So bulkhead isolation is isolating certain portions of your application from taking out other portions by reserving capacity, resource, or other stuff. So the analogy comes from submarines, where if a submarine springs a leak, they block the bulkheads down. So flooding one portion of the submarine doesn't drown all the people, because that'd be a really, really bad idea. They only drown the 2 or 3 that are near the leak at the time. And you can do this with your software. So isolating elements of an application to pools so that if one fails, others continue to function. You can do this with partitioning across hardware. You can do it with resource groups. You can do it with availability zones in Azure or any of the cloud vendors. When a single process faults, multiple failing calls backing up can easily swamp resource on a machine. A faulting downstream system can also cause a backed up set of failing upstream calls. So bulkhead contains a set of actions in a fixed size resource pool, isolating them from failure. And literally, in real practical terms, make sure you partition your system so that all the different bounded contexts can't sucker punch the other ones offline. You don't want your search function taking down your shopping basket or your shopping basket taking down your checkout, because those things can reasonably fail in isolation of one another. Which brings me really neatly onto the notion of graceful degradation. So when I normally say that, people think I'm talking about like browser, like capability testing and stuff like that. But actually, it's nothing to do with that. It's about learning what and how to disable portions of your application while still maintaining this concept of upness. So think about multi-availability zone, multi-region data replication is quite a fun one. And degradation as a feature. And I don't mean I'm not going to make that joke. I mean basically design for disconnection. So there's a really, really simple example here. Imagine you've got a login system and a user system, like some kind of user context, and a checkout system and a basket. Those are complete vertical slices through your system. So if you don't design for degradation, cool, I've added something to my basket, the basket's down, nothing can happen. Or I went to click checkout, but the checkout service is down, and this user that has a basket full of things they wanted to buy, because we can't load their address for some reason, that means, well, they can't give us their money. Whereas if you take that same system and design it with data replication in mind, imagine this as a workflow. When you create a user account successfully at some point, and you go through checkout, the checkout subsystem will request the user data from your user subsystem. Cool. It will then store a copy of that data. The next time the user comes back, it will try and make that call again. If that call fails, for whatever reason, what it instead does is says, hey, this is the most recent information we have for you. Can you just confirm it's correct? Now, it doesn't matter. It may be stale data, but you've given the user a chance to recover. They don't care that your user management system is offline. They couldn't care at all. But you've actually stopped your site from appearing to be down by giving them the chance to continue their journey. And you can do this kind of stuff in loads of different places in your software, where subtle data replication and features can be built in to make sure that the users can correct anything that might be out of line. And then you store a message, and when the user system comes back up, you replicate any corrections they've made back through. So it sounds complicated because it is, because you have to spend time and money building those kinds of features to make your systems this resilient. But you do it, and you'll never be down. When I was at JustGiving, because we used to run the tech for the London Marathon and Cancer Research UK, so we had ridiculous, at the time, amounts of traffic on like 12 web servers. We were having like 36,000 concurrent users a second on marathon day. It's a lot. It's a lot of people, and we were terrified about going down because we were physical hardware at the time in a data center. So it was basically a race where we'd load tested all the hardware. We knew where the wall was, and we got to sit there and watch as we edged ourselves closer and closer to offline. We never went offline because we faked it. So we hit the wall a couple of times, and we replicated our donation page as a static page in a content bucket that our load balancer would fail over to. And then that static page posted donations onto a reconciliation queue that we then processed in the background. We never went down on marathon day. The perception was we never went down on marathon day. We went down once, but no one ever saw it. And if the donations still go through and the money's still taken, does it really count as going down? It's just a failure mode. So, I mean, it costs money to set these things up, but it means you're bulletproof. I'll come back. Thank you. Instrumentation is no longer a log file, and this fucks everybody because people don't think about this when they're breaking up all their systems into lots of tiny pieces. So when you broke it up into 30 different components and one of them broke, I hope you know which one broke, because your monitoring isn't a log file, and it's not 30, it's probably 50, and they don't all line up because maybe your network time server isn't quite consistent enough, or there's a little bit of latency, so all the timestamps are wrong, and you can no longer trace calls through your system. So you need consistent error handling approaches for behaviors like this, or you're going to literally, well, figuratively, die the first time you have any kind of unexpected outage. And you need this from day one. You can't retrofit consistent logging. You need correlation IDs across all your requests, and a standardization of headers, and a consistent log aggregator. And if you're thinking that sounds like a lot of work, it's because it is. You can buy it. Actually, hey, we can do a sponsor bit. Raygun is absolutely amazing. And you get the stuff out of the box, and I fucking swear by it. I try and sell it to everyone. They're brilliant. Use Raygun. It's great. There we go. They got the value for money out of this one. Thank you for the pizzas. And you shouldn't be embarrassed by a really well-maintained monolith. And it's almost heresy to say that in 2020 when what our gods and masters Docker have enforced us into splitting up all our systems into tiny Python things that fail on package restore. But you can mature the design of a monolithic system to adapt to the cloud. You really, really can. There are many well-worn architectural patterns that support this. Most noticeably, the notion of ports and adapters and hexagonal architecture. You can start with a big thing and you can snap things off on the edges. This is totally fine. It just suggests that you have to push external dependencies to the edges of your software and make sure the core domain of your software stands alone. You don't have to believe me, though. It's fine. I'm just an unemployed drunk. I mean, it's not like Martin Fowler didn't say it first. You can just Google monolith first, and I presume people believe Martin Fowler at this point. Yeah, move fast and break nothing. Like, fuck all the dude bros in San Francisco that think breaking people's shit is okay. Really, really isn't okay. You want to rework your architecture safely. There's plenty of ways you can do this, and you should do it in production, because you're always testing in production, even if you think you're not, you are. GitHub, quite a few years ago now, had this really great example of running experiments for replacing services in their architecture. So Zach Holman from GitHub articulated it best with move fast and break nothing. So they authored a library called Scientist that allows you to compare the results of one code path with the results of another. Cool, that sounds a bit meta. What that really meant, and their running example, was GitHub's login flow was really, really complicated in that nobody knew how it worked at all. So they wrote a library, and basically all it did is call old login and new login concurrently and measure the results. And they measured the results as they were hacking on prod, literally hacking on prod, shipping their new login thing, until those two lines converge. And when they'd made it work within enough tolerance, they switched the implementation. You can do this stuff. I mean, obviously it's constrained to things that aren't destructive or change data, but even in those cases, there are ways to replicate that problem. There are some ports into .NET land of things called, like the Scientist.NET. I think that was one of Rob Connery's things a few years ago. But they're really, I've used this approach to solve a lot of really, really gnarly things in production, and especially in cases where people are like, oh, we can't replicate this thing, or we can't test this, or we can't replicate the load. Just do it in prod, who cares? And that sounds cavalier, so you can quote me and tell your boss, just do it in prod, who cares? But it's important because it's safe. And that's the message, you can do it safely in prod. And then there's the rise of GitOps. And this is really a hat tip to Heroku and App Harbor for normalizing this years ago. So GitOps is kind of a wonderful source controllable way to capture some of the complexity we're shifting from our applications into our infrastructure. Because the other thing you notice when you split up a system is all of the infrastructure around the system, all your build scripts, all the root definitions and load balancing rules, that's where your software is now. And you have to be able to capture the fact that that's where your software is now. And GitOps seems to be striking this gentle balance between the scripting hell of Puppet and Chef and Ansible with this perfect dream of like seamless desired state configuration. Like, a lot of this ends up home rolled, and there's not only one way, but it's kind of where I'm betting everyone's going to be in the future. And you're seeing it now. Like a lot of these things, when you look at GitOps, it's the least traditional ops approach out of all these kind of tech. So Ansible, Chef, Puppet is basically what your on-prem sysadmins were doing for 20 years, just written down in a script file. I'm not religious, but there's an analogy I always like to use, like if God wrote software, if he existed, apologies to anyone that believes he does, where would his software run? How would it run? Well, it would kind of be on every server instantly, the moment he touched a line of code, if it worked, and if people turned up, it'd run everything, and if no one was there, it wouldn't be running at all. And I feel like GitOps is getting us as close to that weird hypothetical reality of like magic software that scales and scales down, and everything is kind of declarative, and it's a good thing. And while I wail on Kubernetes all the time for being drastically overcomplicated for basically everyone in the entire world, they do GitOps quite well in Kubernetes land, and I think that was probably the thing that's going to make it stick. Oh, cloud neutrality. This is great, given I've just done a double cloud migration for some software that never shipped. Absolute insanity. Okay, so DevOps professionals growing out of traditional cloud, ops roles will always want to control everything, as do programmers. And the truth is, control is bad for you. It's really bad for you. You just hurt yourself with all the flexibility. Control isn't the real key. But when people get into this mindset, we want to be able to control all these things, what they're really saying is, oh, we want to run it on-prem, and maybe on like AWS, and then, oh, but what if we want to go to Azure because like we really hate Jeff? And then what if Azure folds and we need to go to Google, and then Google shut down GCP because it's not got half the market, and we have to go back to, maybe we should do it all in containers and do it all ourselves. So, cloud neutrality is the database agnostic of the late 2010s. I don't know if anyone remembers the great ORM battles of the 2010s and a little bit earlier, where everyone said, oh, we'll use an ORM because it'll make us database agnostic, so when we switch from SQL Server to MySQL, we don't have to change any of the code. And 100% of those projects had to rewrite 100% of the data access when they did it, 100% of the time. Like, it's just bullshit. And cloud neutrality is bullshit. Complete bullshit. All you're doing when you're building cloud-neutral cloud applications is isolating yourself from all of the good features of the cloud you select and paying 100% of the cost of a cloud migration 100% of the time from day one. It's just absolutely intellectually bankrupt as an approach. It's dumb as it comes. And don't do it. I literally just had to do this under duress. And we changed all the software with every migration. It's the third time I've seen it happen. I've never seen the software not change in a cloud lift and shift. So yeah, cloud neutrality, push back on the DevOps guys that think it's a good idea. So, designing for cloud is actually hard. And all the vendors will tell you it's really easy because that's their job. Their job is to sell you their cloud platform and tell you how easy it is and how it solves all the problems you might have in your development life cycle with just 3 clicks. They're not lying. It's better than running your own data center because you're probably really bad at running your own data center statistically, right? Like you're probably not going to be doing really well at that. It is great, but you've got to really, really think about software. You've got to define boundaries in your software, and it's really a thankless task. I often see teams designing software that fails one of the prime directives of good design. What changes together, ships together. And when you start thinking about that, again, I hate repeatedly bringing this back to like Eric Evans style DDD, but it protects you from domino microservices. It makes you think, oh, a microservice is actually a vertical slice. Because if I want to do a change to the UI, actually I probably need to add some logic in this thing. Like, we're not using Lego blocks. These are big slices through the system. They're components. It's very, very easy to fall back to 1990s style n-tiered sliced horizontal design across components, because that's the way computer programmers think. They think about the components they're stacking together and their onion wraps of abstraction. But actually, targeting vertical slices from front to back is much more effective. It lets you scale your teams more effectively. More people fit around the code base. These bounded context-driven vertical slices help you scale along a number of dimensions. It's just as easy to fall into a pattern of premature simplification, building dominoes of nanoservices that really should just be one thing. So what does scaling mean if I talk about optimizing for multiple axes of scalability? And people use scalability as if it's a magic word, like, okay, scalability, does it mean requests per second? Well, yes, of course it means requests per second, so that's scaling in traffic. But does it mean scaling your team? That means how many people can concurrently edit a piece of software. So that's about the surface area of your code and about contention between multiple people working on the same code base. Does it mean the ability to scale your product and your feature set? So for instance, we built scalable software. Cool, product management, like, yes, we're going to do the big launch. We're going to onboard 2 million users. Oh, fuck. What if we need like support for this? Still scalability, same word. And your software has to scale in all of those dimensions in order to survive. So scaling for traffic comes for free on most managed services. You don't have to worry about that. And that's the one programmers think is the hard one. But it's a checkbox and a credit card. Scaling your team is directly related to the code surface area, the size of your bounded contexts, and the design of the components inside them. And scaling your product features is what your business folks tend to mean when they talk to you about scaling, onboarding, support, and the operability of a system. Serverless technology takes the explosion of diversity in the cloud ecosystem and makes it even more myopic. So instead of the risk of driving towards nanoservices, the boundary is now your entry method. With this great power becomes great responsibility. Most of the serverless runtimes are, we're going to go with not very debuggable, if I'm being really polite. So, I mean, AWS is hot garbage. Again, you upload a zip file. I mean, they've got some slightly more good things now, but like AWS Lambda was garbage for about 2 years and is just about acceptable now. GCP have kind of got it right, but it only supports like Python 2.7, 3.6, and Node, but only Node 8 really works, and Node 10's a bit buggy. And Azure mostly get it right, honestly. C# as a first-class citizen, and Node, and Python, and I think Java as well. But without the serverless framework for AWS, Lambdas are pretty unusable. And seeing the logical flow of operations through your code base, because remember, where is your design if everything's serverless functions? How do I look at this thing? How do I debug this thing? Becomes really difficult. Microsoft fare better with their runtime for Azure being locally installable and debuggable, which is pretty good. And actually, the C# instrumentation is brilliant because you can have one coherent code base, you can mark up multiple entry points, and you still get that code topology coherence of looking at a single cohesive app without the, and still be able to leverage the scale up, scale down of multiple entry points and serverless functions. So I really actually like what Microsoft have done today. The first version was garbage, and if you tried to use it too much, you would run out of ports on whatever version of Windows they were running underneath it, which is quite funny. So if you think coherence in code is important, beware of serverless. It's dangerous, like it can ruin the cohesion of your code base. If startup performance is important, also beware serverless. Latency, package restore, compilation time, all hits. And they've optimized this out, so they've got caches for packages and things like that. But for async processing, things that happen on triggers, things that don't require timely interaction for batch jobs, serverless is absolutely amazing. Really, really good. I say the Microsoft runtime's good. I had a funny with the GCP runtime this week, actually. They have an emulator that you can install, like a Node emulator for Google Cloud Functions, except it doesn't behave like the actual Google Cloud Functions runtime, which was really, really great. Thank you, Google. Thank you, Google. Hi, I've just been reading about trailblazing women in science, arts, and politics. Can I tell you about one? No. It's International Women's Day on Thursday. This is still as true as it ever was. Making a website for 20 users, you probably don't need a Kubernetes cluster. Sorry, yes, they're cool. No, I don't care. Choose technology solutions with the knowledge that for every order of magnitude of growth that you ask of the software, your software should change. People always fall into this trap. We're going to build the thing for the next 10 years. How many users you got? 10. Cool, well, the design of your system you need when you've got 10 million is not going to be the same design as when you got 10. That's cool. That's what the original microservice argument was. We will build a thing for what we need now, and we will throw it away when our needs change and build another thing that can cope with that scenario. Believe that your design can evolve. You're not building these wonderful stone tablets that are never going to change. Please don't do that. Don't waste money on things that will never happen. The cloud makes it really, really easy to waste money on really expensive resources by just dragging a dial up. Think. And most cloud technology is barely a precocious teenager, to be honest, especially in open source software. So you have the, you know what this picture is? Really, really weird DVD called like Japan World Cup. It's brilliant. You basically get a load of alcohol and you each pick a horse, and whenever it runs funny, you drink. I can't really explain it other than there's obviously a panda and like an elephant on that thing, and it's one of the trippiest things I've ever done. Yeah, so this idea of innovating responsibly is a concept that I really, really care about, and it's a way to guide how you choose risky technology in a teams. And I read this really great post by someone whose name I've forgotten. We'll edit in the notes. And what he said is he liked the idea of you have an innovation budget of, like, say you got 3 tokens, and you want to use a new programming language, cool, you just spent a token. Crazy new database technology, you spent 2 tokens. Maybe you want to use Kubernetes, 3 tokens, you've got no experience in that. Cool, now you can't pick any more weird stuff until you return one of those things that you spent those innovation tokens on to stability and boring and a place of normal. And when you make those things normal and boring, you get an innovation token back and you can take another bet. And it doesn't mean only use boring things, but also boring things are quite successful. It means innovate responsibly and choose the things you want to take your bets on. And this is really very much a software design manager's job. Like, this is what your boss is meant to really be doing, is saying, hey, are you really sure you want to do this? And then when you say, yes, it's the best thing in the world, go, okay, cool, try the thing. But it's their responsibility to make sure that you are safe, or yours if you are that boss. Basically, your context determines just how much you can gamble. You got deep pockets, cool, go nuts. Oh, and don't spend all the innovation tokens on the same product at the same time, because you'll fail. It's really, really, really not going to be a good time. So yeah, good riddance to infrastructure at AWS. Sorry, Amazon. But no, really, it does. My notes say no, really, screw AWS, but I should probably be more diplomatic than that. It might sound like I'm being overly negative, but this is totally aspirational. I adore the fact that by saying goodbye to traditional infrastructure, we're opening the door to innovation in hosting and hardware. Like, stop pretending we've got servers and disks and networks and things, and people can make weird custom hardware that makes all this stuff even better. Once we start shaking off the old things here and think, hey, well, what we've really got is like processors that we're scaling virtually. Maybe someone can build a specialized CPU that makes them run really fast. Because I don't care about the operating system. Sorry, Windows. Sorry, Linux. I don't care about the hypervisor. What I care about is my code. And I think that's like a really, really beautiful place that we're almost at as an industry as a whole. So by moving up this abstraction layer, we're going to get more innovation. So Spotify were kind of right. Aligned autonomy. You want to solve all the big problems once and once only when you distribute your systems. Logging, instrumentation, all that stuff. You want to pattern them across the entire of your organization, bake it into the DNA of your software. This is what software architecture should mean. This is what cloud architecture patterns means. This is how you build cloud native applications. The irony with many of these techniques is they're just good same patterns for fault tolerant systems. Like, the stuff hasn't actually changed in 2 decades. Just when all that stuff was originally written down, most people really didn't have any need for it and weren't building the kind of systems that needed to be fault tolerant. We were just building e-commerce websites. It's now renewed in importance because the cloud is in its nature distributed and faulty by default, request by request. So, is everything fucked? I've noticed that they censor me on the auto transcription, and there's no checkbox to turn it off. Absolutely not. Like, I actually think we're in the best place we've ever been in the industry, other than maybe Kubernetes. It's really important to realize that you're not Facebook. You're not Google. You're not Twitter. You're not Microsoft. You're not Xbox Live. Some of you might be, but you're not. You don't need big complex things to run systems sensibly. The big vendors have really, really reliable, really pleasant to use platform abstractions that are definitely good enough for most of the software you're building that can scale to billions of transactions a second. And don't quote me on that, but you know, they built all this stuff. I love the cloud. I love that platform as a service gives us this wonderful panacea of developer productivity that's really, really beautiful. And it had an early rocky road, but honestly, everything's really good now. Remember, moving to the cloud is just the start of the journey. And actually, the care that you put into your software as you do it is what will make it a success. And don't lose sight of those North Stars of good. It's easy to get lost with all the technology and all the jargon, but you need to care about your code topology. You need to care about how you capture and instrument your resilience features in the cloud. These are all the non-functional requirements that the conceptual architecture diagrams never capture. Microservices and clouds won't solve your problems by default. We've suffered as an industry by telling these tall tales of success. Stories about the end of the journey, but not the road we traveled. And the number of talks I've been to about successful AWS migrations or successful Azure migrations, parroted at conferences especially, when the people talking about them have like taken a single service and put it into AWS and gone, yes, cloud migration. I'm just like, oh God, you poor people, you're just at the start of this journey. Please don't make it seem this easy, because everyone's going to feel bad about themselves when they have a hard time doing the thing. This is hard stuff, and it's getting easier. You know, I want you to deliver change safely, deliver change honestly, and deliver change fearlessly, protected by cloud architecture patterns. And sometimes that involves leaving the jealousy of trying to be the next Netflix at the door, because you're probably not going to be the next Netflix, and that's okay. I just want you all to be the best you. And I know that sounds like a hippie trippy thing, but legitimately I think we should all just try and build the best software we can build and not stargaze at all the people using stuff that we probably don't need. And that's it. Thank you.